If you're not learning how to build with AI right now, you might be falling behind because the people who are, they're not just learning how to use AI, but they're getting hired to build AI solutions today. This is your shot to get ahead. I'm going to teach you how to build your first AI chatbot using Langchain and RAG, the exact tech that is used in places like OpenAI, Google, and Meta to build real-world AI apps. If you know basic Python, maybe played around with GPT, but want to go deeper, this is made for you. You will learn how to bring your own documents, chunk and embed them into a vector store, and create a chatbot that can accurately answer questions using your real data and not some general AI fluff. Before you apply to your next dream job, run your resume through our free AI resume analyzer. See what you're missing, double down on your strengths, and get an edge in the screening process. Grab it below, it's totally free. Enough theory. Let's get our hands dirty. We're going to build a simple but powerful RAG application, a Q&A chatbot that can answer questions based on the content of a YouTube video, even if that content isn't broadly available or constantly updated online. This is a perfect example of RAG's power in action, grounding an LLM with specific external knowledge. For this demo, we'll use a popular open source framework called Langchain, which simplifies building LLM applications, especially RAG systems. Our mission: ask questions about a specific YouTube video, and have our RAG bot provide accurate answers by looking only at that video's transcript. Before we dive into the core RAG components, we need to ensure that our environment is set up properly. So we need a OpenAI key to work with our system. So for that, let's write a little bit of code. We're going to use the getPass library. This library ensures that your sensitive keys or API keys are never visible in your notebook's output so that your credentials privacy is maintained. So that's that. Let's quickly get a little bit of code to create our API key here and just set our API key to the value that we're working with. So let me run this. I'm going to copy my API key from platform.openai.com. You can create your own key there. That's fairly straightforward to do that. You'll probably need to load a bunch of credits, but really that's about it. With that done, let us install a couple of libraries that we need for this work. So we're going to get a couple of libraries here. I have the libraries defined. Let's create a new cell. So these libraries that I have do a couple of things. And in order to understand what those are, one of the libraries that we have is YouTube Transcript API. This library is our bridge to YouTube, allowing us to easily fetch the transcript of any public video. We also have Langchain Community. This package from the Langchain ecosystems provides a wide array of tools and integration. In our case, it includes the YouTube loader for convenient data ingestion and FAISS vector store. We'll talk about this a little bit later. Langchain OpenAI. This package is Langchain's dedicated connector for OpenAI services, enabling us to seamlessly use OpenAI's all the powerful LLMs like GPTs, etc., for text generation and their embedding models for converting text into numerical vectors. FAISS CPU is a very efficient library developed by Facebook AI and open sourced for similarity search. It will power our in-memory vector database, allowing us to quickly find relevant information. We also have another library called Python.environment. This allows us to load environment variables. This is not a part of RAG, but it's a general Python ecosystem tool that allows you to get environment variables loaded into your environment. So let's install these with this here. Give it a couple of seconds to do this. Now that the libraries have installed, we are going to do some imports from these libraries. To do that, I have a couple of imports defined. I'm going to paste them here. We're going to use from YouTube Transcript API, we're going to get the YouTube Transcript API class. We're also going to take the recursive character text splitter from Langchain text splitter module. We're going to get OpenAI embeddings and chat OpenAI module from Langchain OpenAI. We're also going to get vector store, which is FAISS, and we are also going to get a prompt template from Langchain core. Let's import these. All right. So now we are going to do some direct transcript fetching and processing. So we want to fetch the raw transcript of our chosen YouTube video using the YouTube Transcript API library. We specify the video ID to ensure that we get the correct video's content. Once retrieved, the transcript, which initially comes in chunks with timestamps, is flattened into a single continuous string of plain text. This consolidated text will form the raw data for the RAG that we're trying to build today. So let's take one of the interesting video IDs from YouTube. This video contains information from Apple's event, and we're going to write some little bit of code here. Try, and this is going to be transcript list equals YouTube transcript API dot transcript API dot get transcript, and we are going to pass in the video ID and language. So it's going to be video ID and languages. We want to be specific about the fact that this video was in English. That needs to be passed as a string, en for English. And now let's join this entire list of transcripts into a single transcript. So for that, we're going to get this here. This is a transcript list. All right, what else? We're going to print the transcript as well so that we can see what we have here, and then we're going to write a small exception. So let's print the transcript finally. Print transcript, then accept, or just use this simple exception here. So let's try to get this. See if we're able to get information from this video ID that contains the data from the Apple event. All right, let's run this. All right, so this is the transcript from that Apple event. You can see that this Craig here, one of the well-known people in Apple, high precision mouse, both a super popular computer, and what else? Scroll a little bit below. Mac OS, iPhone, super cool. What else is here? OpenAI, Siri, probably here. This is one of the videos that Apple recently launched on their YouTube channel. With a full YouTube transcript now loaded, the next crucial step is chunking. A raw transcript might be very long, too long to fit into the context window of an LLM, or to be effectively searched. Breaking it down into smaller, manageable chunks, we can ensure that each piece is small enough for the LLM to process efficiently. A vector database can perform more precise searches, finding just the most relevant segments. For this, we're going to use the recursive character text splitter. It's a fairly sophisticated tool that attempts to split the text intelligently, maintaining context by trying different delimiters, and allows for chunking overlap as well, which is a good technique to prevent the loss of meaning at the boundaries. Imagine you have a sentence, I have a cat, she's very playful. You want to remember the context here, and she refers to the cat in this scenario. So that's the idea. So let's write a little bit of code here. So we are going to move splitter equals recursive text splitter chunk size equals 1000 chunk overlap equals 200. So for this demo, we have chosen a chunk size of 1000 characters to ensure each piece is substantial enough to carry meaning, but small enough to fit within the typical LLM context window. And a chunk overlap of 200 characters is added to ensure continuity between chunks, meaning that the end of one chunk is slightly repeated at the beginning of the next. This overlap kind of helps to ensure that the context might span across chunk boundaries, preventing crucial information from being split in half and lost. The same idea that you don't want to lose the meaning of the cat in this entire sentence if I am talking about cat extensively for that matter. So let's create our chunks within our code. This is our splitter, and this is our chunks. And we are going to create one more cell here to check the length of our chunks. Let's split the text and let's see the length of the chunks. The length of the chunks happens to be 32, and that's where we are at. Now that our transcript is neatly divided into chunks, the next critical step for retrieval is to transform these chunks into numerical representation called embeddings. Embeddings are nothing but text converted into numbers, essentially. An embedding model like OpenAI's text embedding 3, there are many of these, but OpenAI has a good one, converts the meaning of each chunk into high dimensional vector. Chunks with similar meanings will have vectors that are numerically close in this high dimensional space. So generally, the idea of embeddings is that convert a text into a number, and that number is spread across multiple dimensions, 40 dimensions, 50 dimensions. Um, these embeddings are then stored in a vector database, and that's the point of vector databases, to store embeddings, which is very specifically designed for efficient similarity search. We'll use FAISS or Facebook AI similarity search as our in-memory vector database, providing a fast and effective way to find the most relevant chunks when a user poses a query. So we're going to get some embeddings here using embeddings equals OpenAI embeddings. This is the definition, and we're using the model text embedding 3 small. And to create the embeddings out of this, we are going to take from the vector store FAISS dot from documents, and we are going to provide the chunks that we got and that we created, along with the embeddings that we have downloaded from OpenAI. With that said, let's run this. All right, now that we have created the vector store, let's quickly look at a couple of documents that we have stored with their index against their doc store IDs. Let's see. You can see that we have a couple of indexes here, 32 specifically, with indexes ranging from 0 to 31, and the sentences stored in them. Now, with that said, we're going to talk about the second bit, which is retrieval. Our vector store is created. Now we can start asking questions. So we're going to configure the retriever and test its search capabilities. So this is our vector store ready. We will now turn this whole system into a retriever. The retriever's job is to efficiently search our knowledge base, which is our vector store, which you can see here, for chunks that are most relevant to a given query. We configure it to perform a similarity search, which means it looks for chunks whose embeddings are numerically closest to the questions or the query's embedding. We also specify some value like what are the top 4 or top 5 or top 6 similar chunks. There's a number that we specify to get the number of chunks that are the most similar to the question or the query that we have. After we set up the retriever, we can immediately test whether it's effective or not by passing a sample query. This will allow us to see which pieces of information it identifies as most relevant to our question. So let's see how to write the code for this. Let's come back to this, create a new cell here, and this is a retriever. Retriever has a search query, and let's see what we get here. So going to create a retriever. We have vector store dot as retriever, search type equals similarity, and search keyword arguments k equals 4, or the value of k is mapped to 4, k more 4 most similar sentences to the question that we have. Let's ask a simple question. Retriever dot invoke, and let's ask a question about DeepMind, and let's see the kind of sentences we get from this. I'm going to run this. Let's see what we get. Okay, so this year describing our latest release of both on-device models and a private cloud compute model. Cloud compute model is much larger, GPT-4o. This is our attempt to make Siri more interactive AI companion, etc., etc. This is using generative AI, etc., and a bunch of other things here. So we're trying to find the most similar four sentences that we stored from our document initially, which happened to be a transcript of a YouTube um, video. All right. Now, with that said, the last part that we really want to do here is to use an LLM to take this information that we have on our screen here and convert it into something more sensible. For that, we're going to use the LLM. And while the retriever did find us the relevant chunks based on the question that we asked, the large language model still needs very clear instructions on how to use that information to answer the question that you asked. This is where a prompt template comes in. It allows us to define like a structured prompt that will be sent to the LLM, incorporating a bunch of things like system instructions to guide the behavior of the LLM. Act as a helpful assistant, answer only from the provided context, things along these lines. The retrieved context that you can see here on your screen, that's something that we get and we need to pass to the LLM. And the question that the user asks, the actual question that we want the LLM to provide an answer for. This template ensures that the LLM stays grounded in the information that we found from the retriever and avoids hallucinating or using its general knowledge, specifically in these cases when we want only answers from our own documentation or our own context that we have provided. So, for that, let us create a new cell and use GPT-4o Mini, great LLM, also fairly cheap for demonstration purposes. All right. What we're going to do is that we're going to use a prompt template here, and I have that stored so that we can save some typing time. Okay, so this is your prompt template that we got from one of the modules earlier. The template says you are a helpful assistant. Answer only from the provided transcript context. We're telling the model that this is a transcript that you will get access to. If the context is insufficient, just say that you don't know instead of cooking up an answer that I don't really want. And then we provide the context here. And this is your question. This is something that we'll pass later. So let's first create a prompt like this. And then we are going to formulate the query and retrieve the relevant chunks. So now we're going to define the specific question we want to ask our YouTube Q&A chatbot. Now, once we set the question, we use our configured retriever that we did in the last step to search the vector store for the most relevant document chunks based on the semantic meaning of our question. Retriever.invoke, again, is the idea that you saw before. It's the core of a RAG's retrieval phase, getting us the exact pieces of the video transcript that are most likely to contain the answer. So let's ask a good question. In this scenario, it could be, what is Craig talking about in this video? So let's ask this question. And to get the response, we're going to use retriever.invoke question. So it's aware of the person Craig. It's also aware of the fact that there's a video. Let's see what we get. All right. So we clearly have something that has been retrieved. Let's print it to be able to see it. So we are going to use a simple string method here in the cell and print it with content context here. All right, so Craig says you can see that the Craig is showing up here. I'm sorry, thank you guys, etc. Again, there's much more here, Joanna and Siri, and then there's a little bit more information here as well. This is fairly big. There is more information here, but let's make sense of it. This is exactly what we got from the document. Now, to finalize the output in a format that we can consume, because there's a lot of information, I would like this to be summarized by the LLM. We are going to bring everything together we have a prompt template that we created a while ago, and we are going to insert this context text into the prompt template and the question from the user. That is the final prompt that we will be sending to the LLM to generate the accurate and answer that is grounded in your facts. So let's create a final prompt here. We're going to create final prompt and also print it directly. Prompt. All right, let's see. What do we get? All right, so the entire thing has now your helpful assistant, and then we have also added the context, and we've also added the question as well, or what is Craig talking about in the video. So this is user's question. We have added the context that we have obtained from a retriever, essentially, which contains information that is stored in the vector store. And we have also provided the right instructions to the LLM. So now is the final part of this, which is generation. The LLM is going to take this information and give us something that we need. So this is basically the culmination of our RAG pipeline, with the final prompt assembled, combining your question, the LLM's instruction, and crucially, the relevant context retriever from YouTube Transcript. We are now going to pass this to our LLM. The LLM is going to process this prompt and generate an answer that is not only coherent, but also well written. So it needs to make sense to us. And it's also going to be grounded in the specific context that we're providing. So let's run the last bit of code to see what we get. All right. So the LLM has summarized this for us, stating that Craig is discussing the development and progress of Siri, particularly in relation to the announcement made at last year's developer conference. He explains that while they showcased the smarter AI-driven Siri with new features, some aspects were not ready for release due to quality concerns. He emphasizes the importance of delivering a reliable product and things along these lines. Craig also mentioned. So you can see that we took this information present in a YouTube video. We created chunks of it, and we stored this in a vector database. We asked a question and got very relevant information out of the vector database. And then that information is what we passed into an LLM using the prompt template that is a part of our Langchain. And we put all of this information together. LLM did a summarization of this information and has provided a complete, sensible answer to us. That essentially sums up how a RAG, or a retrieval-augmented generation, works. And now you know. Still here? Great. Because the next leap in AI isn't chatbots, it's agentic AI. Autonomous systems that plan, reason, and execute. If you're not learning it now, someone else is, and they're getting hired first. Join our free webinar to understand how engineers are building real-world agentic systems and how you can do it too. Link is in the description. Don't miss it.